long range. But a lot of what I'm going to say there won't make sense unless I talk about the long range icing model for a while. So I'm going to mention two papers, one recent one and one new one. One old one and one new one. So this is one during my PhD, and then this one I just came out with 3 people in France, one of whom is applying this year. So an important thing to note is that these are non-local CFTs. Different communities define locality and non-locality in different ways. So in quantum information, you might say that a non-local QFT is something where entanglement entropies have volume laws instead of area laws. But the definition I'm going to use is that non-local CFTs are CFTs with no stress tensor. So we're familiar with the idea that if you write conservation of energy in this local form, you can integrate both sides over space and find that energy is globally conserved. But the implication doesn't necessarily go the other way. You can have theories where there is a conserved energy, but no local form of that conservation law. So in particular, it might be the case that you can look at the flux of area, the flux of energy out of some ball, and find that it's something that can never be determined if you just have information from the surface of that ball. So that's what I'm going to mean by a non-local CFT. And it's not so exotic because we've all seen a simple example of a non-local CFT. We saw that in Virasoro's talk. And that is a generalized free theory. And it has a very simple definition. So first, you specify power law in the 2-point function. Second, you specify that endpoint functions of the fundamental field are given by weight contractions. And finally, you specify that composite operators are defined points of them. And it's easy to see that for generic delta chi, this theory doesn't have a stress tensor and a spectrum of local operators. Because you can look at, I get the coefficient wrong. You can look at the lightest operator of spin 2 that you can build out of these fields. And if you demand that it's conformal primary, you'll get this. And of course, the dimension of this is 2 delta chi plus 2, which is not D. So it's not a stress tensor. Now, this non-local CFT also has some local descriptions. So one of them is a trivial defect, which is D-dimensional. In some higher dimensional space, where the higher dimensional field does have a stress tensor, meaning it is free. Another local description is as the boundary theory for a free scalar of the expected mass in EBS. And the thing about, like, one nice thing about non-local CFTs is that once you know one example, you know many, because you can introduce local and non-local CFTs together and flow to the infrared, find new fixed points. So consider some local CFT which has some relevant operator. And couple it to a generalized free field. So it's convenient here to choose the dimension to be such that the relevant operator in chi gives you something weakly relevant. So this thing for small delta. And then this interaction generates a weakly coupled flow. And then in the infrared, you end up at a new non-local CFT. And this construction is going to come up again and again. So that's generalized free theory. We might think of it as something modern. That's defect, informal field theory, QFT and ADS. These are sort of things that have become popular within the last decade. But non-local CFTs have a very long history. So you can take a spin chain first written down by Dyson in the 60s. Which looks like the Ising spin chain, except you sum over all pairs, not just nearest neighbors. And he looked at one dimension where you can sometimes do things rigorously and showed that this has second order phase transition. And that was very unusual at the time. Nowadays, we would say that a 1x1 traceless stress tensor is just zero. So any 1D CFT is non-local by definition. But back then, the arguments were more along the lines of whether you have to renormalize quantum mechanics. So this is positive. Yes. Yeah, I'll say a bit more about what this is. But it's yeah, it's CFTs labeled by S. So yeah, it's in some sense it's even more surprising. It's a non-isolated fixed point. Quantum CFTs. So if you only had nearest neighbors, you would not be able to get a second order phase transition in agreement with the fact that 1D CFTs cannot have a stress tensor. So this was sort of the first appearance of a non-local CFT in the literature. And it's much more closely related to generalized free theory than you might think, because you can use the perturbative normalization group to study this in the continuum. And this was first done a few years later by Fisher, Ma, and Nickel. So, we wrote down this non-local action. You can have its exact same power. So that's why it equals S. This turns out to be the action of generalized free theory. So generalized free theory, even though it's not local, it has a Lagrangian. It's just something where you have to integrate it twice. It's easy to work out. D minus S over 2. And then what they proposed is you can trigger a normalization group flow with the usual phi to 4 interaction, which is local. And if you want this to be perturbative, then you want epsilon to be small, where epsilon is 2s minus d, because then this would be very close to marginal. So it was also recognized early on that if you make S very large, then this becomes a very sharply peaked profile. And even though you're summing over all sites, the physics starts to look like what you would expect if you just summed over the nearest neighbors. So there was an expectation that at a sufficiently large S, there would be a crossover to the short range Ising universality class. And if you go looking for non-local CFTs that are close to the Ising model in some sense, then you can write down something else. Write down a different generalized field theory to take something of dimension d minus s over 2. Sorry, d plus s over 2. Then you take the Ising model, where the scare quotes mean that it doesn't really have a Lagrangian. We're just taking the tensor product of this Lagrangian theory and abstract theory. And then your interaction would be just this one.
If you take S very large, then the property that it has a second order phase transition D equals to 1. What happens to that?
That would disappear.
There's no transition, right?
No, for this, it has, right? It has a second order phase transition equals.
The phase transition exists in some window for S,
Okay.
and it stops as the same. That's gets there. Yeah, this is actually the subject of a recent paper by Dario Edo, Dalmil, and Fumina, which I won't have time to talk about. So we have these lines of fixed points. So here you can go from s equals d over 2, where epsilon is 0. All the way to this value. Where this becomes marginal. And then we have some RG flows induced by phi to the 4, which are very short around here and then non-perturbative as we move away. And then we can also draw a diagram like that for this theory. So we have a line of fixed points that we perturb away from with short but increasingly long flows here, where the perturbation is sigma times chi. And it's quite natural to conjecture that these actually lead to the same fixed point, so that you get a weak strong duality. For values of S where this is strongly coupled, you can get a weakly coupled description here. Values of S where this is strongly coupled, you can get a weakly coupled description there. So this is what we did in 2017. And there are 3 main pieces of evidence. So one is that you can integrate out chi to generate a non-local effective interaction for sigma. And the one you generate is nothing but this one, where you have d plus s in the propagator. Another piece of evidence comes from looking at protected operators. So whenever you have a non-local kinetic term, so something that's quadratic and non-local in some field, you're not going to be able to generate counter terms for it using local interactions. This is like easy to convince yourself of when you start writing diagrams. And that means that these dimensions, d minus s over 2 and d plus s over 2, they are exact to all orders. So you would have a zero loops exact operator in both theories. But you can also vary with respect to phi and get a non-local equation of motion. So you get something that you write in this way, showing that the dimension of phi cubed is protected as well. So this would be epsilon.
Is the RG equation local?
The RG equation. Is that, you mean the Cohen semantic equation?
Yes, I mean, we're looking to the fixed points equation for so that equations are local.
That would be local because we're still renormalizing local operators, even though there's no stress test.
But for that, we need to add complex terms which has to be local. Okay.
Yeah, the counter terms would all be local. for the operators that do renormalize, so they're the composite operators.
So yeah, I think I'm some very trivial. How do we know things are going through the same points?
Well, we don't know that, but
You're saying that this is so that's a thing. So you want to trigger flow there and want to do something to this phone those kind of. Is it the observation that it's all close to the same?
it. Yeah, it started off as an observation that it would be very consistent for them to flow to the same thing. And then I guess you could say that the bootstrap results later on have are also suggestive that.
So the things that are different here are in the initial seed theories. This have plus S instead of directly minus S.
Yeah, but S can be freely varied.
Yeah, sure. And I also just what the minimizing was. And there's something that we are not specifying yet, or what exactly?
No, this is literally the critical ISIN model.
Oh,
Yeah, so you start off with a tensor product of abstract CFTs, one is local, one is not, and then you couple them to make the whole thing normal.
why the codes?
Because there's no action.
Okay.
Yeah, non-Lagrangian theory.
Okay.
But this is like the critical point of the short ranges.
Yes.
So why can't you write an action for it, like some 5-4 or something?
You can write a Landau Ginsburg
Right.
procedure.
Yeah.
Yeah, but that's that's not the same as an action for the strongly coupled fixable.
I see, that's what you mean, okay, fine.
Yeah.
No, just one thing. So the D here is one or it's arbitrary? You know, it's.
This D is say anything where the short range critical ISIN model exists. So between 2 and 4.
So this is kind of flowing, you are saying it would be valid in any dimension.
Yeah, that was our conjecture.
I see, Right, and this lambda is 1/G, is that right?
No.
Is that,
I mean, one becomes large when the other is small, but we don't have. I mean, first of all, you would need to even specify a scheme for that to be meaningful. But in any of the familiar schemes, we don't have a good sense of how they map to each other.
So just going back to what he was asking. So for the seed theory, you should be able to write down the result. Right? When you're not perturbing it, so this just away from the critical point. So when you start off, you should be able to write down what the icing is.
Yeah. There are UV actions which flow to the icing model.
yeah.
That's for sure.
I guess the point is that if you want to specify the UP action, you need to literally specify all the terms like 5-6, 5-8 and all that. Ultimately, everything you flow to the fixed point, but the specification is not right. So
This integrating of diagonal can not made actually reverse. I mean, if you imagine, as they're saying, right, we do the action for reasoning and the couple is flow, but can I not just do the path into a for chi exactly? Why don't the limits compute, like doing the RG missing and integrating out the command chi?
We think they do, but how are you going to do calculations once it's a non-local kinetic term you generate? Show that it's a sigma. So maybe I should specify another small parameter. Let's do. So. So now there's another equation of motion. We just change S to minus S. Get this. So now sigma is 1 loop exact. So there's a matching of protected operators. There are even more protected operators of these theories, namely odd spin operators and equal BE of sigma, right? But I won't get into that. There are a lot of protected operators you can match. And the real clincher was
Sorry, my question, I think you explained it already, but so you're saying these guys are protected because the kinetic term is long range? Is that the?
that's original. Yeah, and there's one more.
But that's my confusion, sorry, I'm sorry.
No,
But suppose S is pushed to a large number, it's a free parameter, right? Suppose S is pushed to a large number, let's say S is 4 and D is 1. Then it's a local theory, then why should these guys be protected? I don't understand, so.
This is local when S is 2. But a little bit before S is 2, you're gonna hit this value for delta is 0. And then, yeah, and then it's sort of like Prashant's question, the line of fixed point, plan.
I see it. So you're assuming when you're starting this that this is a small parameter or something, and then maybe to control the RG, and then ultimately, if S grows larger, maybe you do some strong couple thing, and then you don't know about the protection. Or
Well, we know the operator that was relevant before becomes irrelevant, so dialing S just stops changing the theory you're in, and you stay stuck at that one.
no, I guess I'm just confused about this long range protection mechanism, because of course, if S is pushed to a high enough number, the theory is not long range, so then things cannot be predicted. So it should somehow come out with the equations, right?
Yeah, the theory becomes not long range because this is irrelevant, so you flow back to a decoupled short range
Okay, okay.
or less field. Thanks.
So that's a 3 times sigma, right? Equation.
Yeah, that's right. So I want to mention one more piece of evidence, which is that if you believe the lower of this becoming short range, and therefore recovering the short range Ising model, but you're suspicious that there's going to be this generalized free field as well that allows you to make this nice perturbative description. Your fears can be allayed by noticing that the stress tensor, as you go towards this point, needs to split into a set of states that form a short multiplet and a set of states that form a long multiplet. So said another way, when you turn on this coupling, the lightest spin 2 operator needs to pick up a divergence. You have some constant, you have the coupling, and then you have something whose quantum numbers have to be up by 1 and down by 1. In the 2D Ising model, this definitely doesn't exist. In 3D Ising model, this almost definitely doesn't exist. So you need to introduce new degrees of freedom. And the best way to do that is to introduce chi, because then what you can write down is this conformal primary.
So sorry, can you please repeat that argument? Why this was from the statements and then how do you get?
So as soon as you switch on G, you have no stress tensor anymore. You just have a spin 2 operator with a dimension a little bit above D. So it's not going to be conserved. And then you can imagine that if you dial G back to 0, the number of states has to stay the same. So this divergence, which no longer appears in this equation, has to still remain an operator in the theory. And then you can justify the fact that chi hits neither, because if it weren't there, you wouldn't have such an operator. So this is the recombination idea that Slava and Zhongming used in 2015 to find an alternative, like slick way to get one loop on almost dimensions and the epsilon expansion. So now that we know this duality, there are 2 directions you might imagine. One is to really push the long range IC case, use your knowledge of the duality to try to get some non-perturbative understanding of the model using from a bootstrap or some other methods. And I'll probably just mention that for a couple minutes. But the other direction, which is the main thing I want to talk about, is looking for other examples of dualities like this in order to bring more models under control. And a very natural set of models to try this on would be the higher minimal models in 2 dimensions, of which the critical IC model is the first case. So to this end, there is a Landau-Ginzburg description of higher minimal models, which I think Koshik mentioned in his talk. And has a little kinetic term. And then it has something where you skip a bunch of relevant operators and get some finely tuned flow. So Semmelogikov conjectured that this flows to a critical minimal model labeled by M. And just to remind you of some data that these minimal models have. Have this central charge and this normal weight. Where this is critical icing, this is tricritical icing, this is tetracritical icing because we're going to mostly care about diagonal case. So, and once you do this, you can define a flow which gets you to something that you would call a long range minimal model instead of a short range one. And that is contained in the usual way, where now you integrate twice. And then you do 2 plus s because you're in dimension 2. And if you look at the conjectured mapping in this Landau-Ginzburg description, the field phi becomes the operator phi 2, 2. So the 2 Katz indices would be 2, and therefore you're led to a conjectured duality. You have the chi field changing s to minus s. Then you have the minimal model by M. I don't know why I'm writing this. D everywhere. And it's 2, 2 operator spin field times chi.
You define this tricritical Ising model for this M equals 4.
Yes.
So what? So you just change the operator that you are using to perturb, and then it becomes a tricritical. What is the definition of tricritical in this sense?
On the lattice, it comes from the dilute Ising model where you consider vacancies as well. But that's not going to be important for us. For us, we would have this operator whose correlation functions are now the ones appropriate for M equals 4 instead of M equals 3. And they're still exactly solvable. So you can do perturbation theory, for example, when G is small, and be able to input information about what the minimal model is. Does that answer your question?
So for the tricriticalizing CFT, there are 2 relevant operators, and you can use the second one to make the phi 4 term vanish. and then the 5-6 is the relevant guy, and the others are irrelevant, I guess.
So why is not 5-4 there? I thought that.
Because you have two relevant directions, so you
Yes.
can use them to fine tune 5-4 to 0. And then we land in a different fixed point.
Yeah,
That's
if
my
5-4 were there, then you would flow to.
Exactly.
normal
Then we
way.
flow to Isaac.
Okay.
Yeah, so in an RG diagram, joint critical would have one stable and one unstable direction. These higher minimal models are all increasingly unstable. And one reason to be interested in this, something where M is arbitrary, is being able to take M arbitrarily large and seeing what happens. So if you expand this Katz's formula at large M, you can see that as M goes to infinity, the scaling dimension here is very small. And we expect phi Q2 to be connected to phi on the other side. And again, if M is very large, then for this to be a marginal operator, the dimension of phi has to also be very small. So here, we had a dimension of this spin field going from d over 4 to delta sigma, so like 1/8 or 0.518, a big shift. Here we're going from a tiny number to a tiny number. So we might imagine that this line of fixed points becomes very short, and then we can develop perturbation theory around both sides and actually make it work for unprotected quantities. So you wouldn't even need the weak strong duality. Both types of perturbation theory would be valid everywhere, and you would actually be able to prove the duality. Now, that was a question we asked, and the answer turned out to be a resounding no. So we cannot prove this duality. We don't know how to yet. And the reason.
Sorry, one nice question. So when you push M to be very large, C is still just below 1, right? We don't hit 1.
That's right.
Because then it's something different.
Yeah.
Or another very nice thing. So I mean, just to get the picture a little bit clearer. In the sense that if you were able to prove that these are equivalent, what's the sort of goal of it in some sense? I mean, you are say we get the economic state what are you going to do with them?
Yeah, so our main interest wouldn't be the large M case eventually, because these are very unstable multi-critical models. But it would strengthen our conviction that the duality is true for small values of M, which are more reasonable. So one reason to care about them is that you could potentially make them experimentally. There are some groups that have come close. They've made other long-range CFTs in the lab. And another reason is this idea that it's hard to rule out non-local theories in the numerical bootstrap. Even if you're looking for local ones, that you'll sort of often be contaminated by these solutions unless you do a lot of work. So it's good to understand them to be able to work with them.
Maybe another interesting thing is that it does give you some sort of a classification if this works of long-range critical CFTs. I mean, in some sense, it's not obvious that if you do this, these are stable critical points, right? So I guess that's what we're trying to prove.
You mean in a sense of like scale invariance and mind conformal invariance and these things? Yeah, that's the mission. So I just want to mention that if you want the dimension of this coupling to be epsilon, like it is in the usual epsilon expansion, then this large M limit means you're taking epsilon to 2. So we want to compute some perturbative quantities and see if in the large M limit, things are still small when you set epsilon to 2. That's the question. So the first thing to do is perturbation theory around this end, whereas everything's Lagrangian. And Yeah, I'll just write one of the simplest results. I don't need to write them all.
Only just to understand from this picture, if I just go back to the Hamiltonian, it's okay. Yeah, so that's, yeah, we all remember the Hamiltonian. Then if you just put vacancies there, you're saying that there might be a way to reach this long range n equal to 4 minimum.
I think so.
Yeah.
I'm not aware of work
Okay.
doing that on the lattice, but it sounds reasonable. Good, so we can get a beta function for lambda. And we computed it to 2 loops. And these coefficients, they are complicated sums where the number of terms grows with m. But luckily for large m, you can get saddle point valuations of them. And what we did then was we looked at a critical exponent, which is one that you can find as soon as you know the beta function. It's scaling dimension of the perturbing operator itself. Just going to be the dimension of space plus the derivative beta function of the fixed. So in one loop, you got this, which is pretty universal. And then the interesting stuff was and if I've done this right, you can use Stirling's approximation to show that this coefficient diverges with m, which means the perturbation theory is sick. If you wanted to set epsilon to be 0.001, something that we usually like to do, gets a numerical approximation, there's going to be some large enough m such that even that is a bad approximation. So our goal of being able to get controlled perturbation theory around here, that large m, did not work. So I want to discuss perturbation theory around the other side now, which is more abstract, because you're perturbing around a non-Lagrangian, or something that's not Lagrangian in the usual sense. And
Just for clarification, so you went to very high, large value of n, so that those dimensions are small. So,
yeah, we went to a large value of m.
but why is it helping? Why are those large dimensions helping the computation?
They don't help. So what helps is the fact that you can use saddle points on A and B. But I guess that's an objection because I wrote here the dimension of a heavy operator in some sense. I mean, it's, yeah, when we take m to be large, we have some number of fields here that is also large. So maybe you could say, okay, perturbation theory is not controlled for this operator, but it might be controlled for other ones. That doesn't seem to be true either. So maybe this argument is too fast.
Some kind of double scaling with n and epsilon, so make n large, but not as large as well, where epsilon still has these in there. So.
We couldn't find a way.
Can you remind me what's the behavior in n of this budget level functions? That's large enough. It's is it power law, is it exponential?
I think it's a power law.
Then maybe there's some scaling. You can scale n with the power of 1 over epsilon sufficiently small that it's still small.
Yeah, these double scaling limits work nicely with Feynman diagrams where you can predict, maybe not coefficients, but you can predict at all loops certain powers that are going to appear. Yeah. I mean, the vertices that don't just have 4 legs, but have arbitrarily many legs makes this hard.
Sure.
Perhaps you could do it.
Well, I thought the tunable, there is only one tunable parameter here, which is m, right? So how do you do a double scale? You know, usually when you have 2 parameters, you can like scale both and keep something fixed, like. I don't understand this point.
There's a coupling constant and there's also n. I think it's similar to like a tough limit. Like setting this guy times n to be fixed or something. But there's going to be further evidence that perturbation theory breaks down large n when we look at this flow. So for this, we should use the framework of conformal perturbation theory. And to be very quick about what this is, it says that to get endpoint functions at some coupling, what we want to do is insert an exponential that happens to go tell us to do. And Taylor expand.
Sorry, when you're using this now, are you still perturbing around n tending to infinity? Are you still, like, is that how you're going, or you're going from somewhere else?
So there are a few different orders in which you might take the limit. So to start, let's say I'm fixing them to be some large finite number and then perturbing in the coupling.
Perturbing in the pocket.
Yeah. So the 2-point function, for example, 1 minus g naught times an integrated 3-point function. The integrated 3-point function for a marginal operator will diverge. And if you say that these positions have some UV cutoff, they don't get closer to 0 than the scale A, then it's going to be something like, I think it's pi. Pi times an OBE coefficient times this log A divergence. And of course, the way you deal with this divergence is you use the fact that this Bayer coupling is not the same as the normalized coupling, and then you get a beta function. Normal conditions. Yeah, so you get this kind of RG in one loop. But looking at the form of this, we have operators that are both odd under a Z2 symmetry when we perturb. So these OBE coefficients are going to vanish, and we're only going to get something that's non-trivial at 2 loops. So this comes from integrating a 3-point function and using conformal invariance to fix the points that you no longer have to integrate. At 2 loops, you're going to have a regulated integral of a 4-point function. Where we subtract power law divergences. Then here's the development of this. And these integrals of 4-point functions are very messy. It's led to a lot of pain and a lot of papers about conformal perturbation theory. And I want to say a little bit about some techniques for getting around this pain, which might be new, which came up in this work. Yeah, so. Yeah, I'll just write an example of a beta function that we worked out in this paper in 2017 using conformal perturbation theory.
Sorry, I have a light question. So suppose you put some large M and then do perturbation in G naught, perturbative RT in G naught, right?
Yeah.
That's what you're doing right now. So why can't I just use standard perturbation in momentum shell? I mean, what advantage does this conformal perturbation theory give? Is the
Well,
is it the same thing?
it is the same thing when you're in the Lagrangian theory,
Okay.
but the decomposing correlators into propagators using Wick's theorem doesn't work if you're using an abstract CFT here. Yes. So it's a generalization of the usual perturbation theory.
I see.
So for long range Ising, m equals 3. We got some beta function, which of course does not have this term, which vanishes by symmetry. And then the next term it has is 1.268, the numerical result from doing this integral times g cubed. So this has a real fixed point. G squared is positive when you set this to 0, so that's good. And what we did this year was find a large M beta function, and now we can express it in the. And that also has a real fixed point. And the way we got this at first was very brute force. We did. We looked at this g cubed coefficient. We went from m equals 3 to something else. Yes, it's 5. Yeah, it goes from like 1 to 5. So, well, 5 words. Yeah. So we got a familiar number as a check, and then we got it to go down like 1 over m squared, and then we fit a curve to this, and we saw that the coefficient was very close to pi squared over 2 over 2, and then we got this as injection. So not something rigorous. But then we can do the same thing with anomalous dimensions, and I'll just write the result. So a reasonable set of operators to get anomalous dimensions for are the ones labeled by Katz indices. So they're primaries under the Virasoro symmetry that the UV has, even though it breaks in the IR. So I'll write that formula at the fixed point. So the two-loop anomalous dimension is something that grows with m. So that's also bad news. If m is infinite, then we can't set delta as these 0.001.
You need to solve a large mixing matrix for this because there's degeneracy for R minus S fixed.
No, there's degeneracy when m is infinite, but we're taking m to be finite at every step of the calculation. So that you're predicting something that's going to happen later in the talk when I try to improve upon this brute force numerical equation. So it looks like perturbation theory at large m is bad news around either side. But now we can use the fact that this is not the only long-range minimal model we could write down. We don't have to couple chi to phi 2,2. We can couple it to another Katz table operator like phi 1,2. And there are two motivations for that. So first, it actually came up in a paper I wrote a couple of years ago doing the numerical bootstrap for the long-range Ising model. So we'll just sketch one of the plots from that paper. So we have this ratio, and you may be able to find the ratios. This is some R times the function of the quantum numbers of O. So when I said there's a lot of protected stuff in the long-range listing model, this is part of what I meant. It's some exact ratios, and you can scan over this R, which is not known, but it's built in L. Scan over it, and then you can say, what is the maximal gap for spin zero operators that are protected? And you make these gaps for many values of S because you input the external dimension of sigma or chi in the bootstrap.
Can I ask a question?
Then you get this spike thing, yeah.
Sorry. So the numbers that you computed there was because you knew the 4-point functions in minimal numbers.
Yeah, that's a good point. So these 4-point functions, we know them as we know how to write them as a linear combination of Virasoro blocks. And the Virasoro blocks, because they satisfy a nice differential equation, can be Taylor expanded to high order. So numerically, we can be pretty confident.
So what was O in those cases? So O has to be something specific, right? It's
Yeah.
epsilon.
O is the perturbing operator itself. So this is phi 2 chi. And then this is phi r. So when S is very close to D over 2, very close to 1, you get this sharp spike. When S is a bit larger, we get something wider. And we get some plots that have 2 kinks. And empirically, it looked a lot like the kink on the right was always the long-range Ising model. But what about the kink on the left? So the position of the kink on the left moves as a function of the gap for spin 2 operators that you impose. Whereas this one stays the same. So that's why we really believe that this was the long-range Ising model. You would close this width as you keep raising the spin 2 gap until you get to the one where the long-range Ising model would be ruled out, and then it is ruled out. Conversely, if you lower the spin 2 gap and you make this wider and wider, you can always get this kink to move all the way to the left. And then you can read off where does it fall on the vertical axis. And it falls in a place that is consistent with delta 0 being delta 1, 3, which would be the leading unprotected scalar if the flow you were describing came from phi 1, 2 times chi. So we think the phi 1, 2 chi models, which are the same as phi 2, 2 chi for m equals 3, but different for all other m, we think they're showing up in the numerical bootstrap somehow. So that's one motivation.
So quick question. So for just to understand this, for the Ising tritrix in CF2, what is chi 1, 2 mean? So it's not the spin, it's some other operation.
Right, phi 2, 2 would be the spin.
Right.
I think
So it's some
phi 1, 2
thing or some.
it's another relevant operator.
I see, it's relevant, but
I can't remember if it's set to even or set to odd.
oh, I see. So it might be something.
But yeah, that is a challenge because it's harder to physically interpret this.
Right. So you're saying it may not be even a spin-like object because it might be Z right?
Yeah.
Yeah, it might be like some energy or something. Oh.
Yeah.
So this motivator was factorized into 5 and which one?
That's it.
Sorry,
Is there another?
Delta 0, so the spin 0 operator. That's the first one would be established.
And what's this axis, x-axis?
It's a ratio that appears in something you derive using non-local equations of motion, or bulk locality, when you use the fact that generalized free fields part of a defect.
So this is the parameter you can write for certain rule.
Yeah.
And when do they explain it? So once like I came from that.
Right, so when we set the spin 2 gap to be something reasonable, we find an allowed region that has 2 kinks. And as we vary the spin 2 gap, the left kink is going to move. And for an extremely high gap, it collides with the other kink and the models disappear. For an extremely low gap, i.e. spin 2 operators start at 2, consistent with the local field, it moves to the left and it attains a vertical position, which is close to that of the 513 operator. And we know that the OPE of 512 twice has the identity in the 513. So that's where the conjecture came from.
So the kinks collide, it has to do with this fact that you take S to be very large and there is only one.
S is fixed, so whether we're getting this plot, or this one, is fixed by the external dimension of sigma and chi. But they collide because less and less stuff is allowed as you make the spin 2 operator gap large. Like as an extreme case, there's this bound on like going back to the early days of the bootstrap, there's just this linear bound where it's saturated by generalized free theory, and if you try to ask your CFTs where the spin 2 gap is even larger than it is in generalized free theory, then you just don't find it. So that's basically what's happening. The kinks collide and you stop finding solutions. So some numerical results made it interesting to look at phi 1,2 chi after we looked at phi 2,2 chi. And a post hoc motivation is that the large M behavior here is going to turn out to be much better.
Sorry, just to be completely clear, so if I think of the primaries of your like conventional minimal model, phi 1,2 is heavier than phi 2.
Yes.
That's correct, right? Okay, so maybe that's important in somehow controlling the perturbation. Is that roughly the thing that's happening here?
It could very well be.
Yeah, okay.
So now over here, I'll write the perturbative results for phi 1,2 chi. That's what it means. So now it blows up with M, but that doesn't matter because it's a beta function. It's need to do something scheme independent. Here's where the interesting stuff is. So for r less than or equal to s, you get either a positive or a negative power of s minus 1 over s plus 1, depending on whether r plus s is even or odd. And for r greater than s, it's the opposite. And this formula looks nice except for two things. It can sometimes be 0 and it can sometimes be infinite, i.e. when s equals 1.
But this is still a large n, and you're saying the leading large n term is just a constant.
Yes, at this stage it's large. Yeah, it's just a large n. So gamma, yeah, so when gamma R1 is equal to 0, this is real, and it holds for all n. And I'll say why at the end of the talk, but a hint of this was when we looked at m equals 3, we also got, in this long range Ising flow, we got the energy operator. So 2, 1, we got that to have a numerical integral which was 0. And at large m it's also 0. So this actually holds apart that all m. And everything else probably just has to be true at large m. And then when gamma R1 is infinite, this is faded because there's mixing and we didn't take care of this result. And yeah, maybe I'll just write what mixes with what. So by R1, it mixes with something of the same dimension, and that thing is R2. So you can check that these have the same dimension. And this is a combination of Virasoro generators, where this is the mode. And it's a combination such that you get a quasi-primary. And if you hit phi 1, 2 with this operator, you generate this. Oh, wait. If you hit phi 1, 2 chi with this operator, you generate this. If you hit phi 1, 2 chi with this operator, you generate this. So the mixing is allowed. And when we actually account for this, we find some corrected anomalous dimension, which is finite. And now that we have some large m limit that's nice, we want to understand how to derive it without doing this tedious numerical procedure. So there are two things you could try. You could try taking the large m limit first when you're doing conformal perturbation theory. So you integrate some large m Virasoro blocks. And the other thing to do is to try taking large m last. So if you take large m limit first, you end up with the problem Antonio was mentioning, which is that there's going to be a lot of mixing. Because if you just had this integral, then you would find that this beta 3 coefficient itself has a log A. So yeah, how do we understand it? If you look at finite m and you calculate beta 3, you get something that increases with m. And that diverges at infinite m. So if you make m infinite first, well, the Virasoro blocks are not going to diverge. Those have nice large m limits, but they're probably going to integrate to something bad. And they integrate to something that diverges in this one. So that's a sign of mixing, because the phi 1, 3 operator becomes marginal. So that is going to have dimension 2 plus a little bit minus a little bit. And we need to consider two beta functions. So this actually leads to something very interesting, which, and I'm curious if it shows up in other perturbative contexts. It's a case where you can get two loop results from one loop. So here we were doing two loop formal perturbation theory because the one loop stuff vanished. But when you introduce this other operator, one loop stuff does not vanish. So you get one beta function like this.
We could form the minimal models by relevant vector operator, the exact same trick.
That is amazing. We should talk. So you get these coupled beta functions. And what you want to do is pretend that delta and 1/m are of the same order when you're getting fixed points. And then at the end of the day, what you should actually do is take this limit. Delta much less than 1/m, much less than 1. Because that's kind of what's going on when you say you restrict yourself to a particular loop order, and then you take the marginal limit. Delta has to be made small first. And there's more mixing to take care of, but and in a few examples we went through the whole mixing problem and we got the right answer. So we got the one loop calculation to agree with the other two loop calculation. For some operators that don't mix, some privileged operators you can identify, we also did the calculation and also got things to match. But this is in the phi12 chi flow. I wouldn't know how to do this in the phi22 chi flow because then you don't have these order 1 OPE coefficients here. You have OPE coefficients suppressed by 1/m. Things become more complicated. So for this, I want to talk about a technique which is not based on taking a large limit first. It's based on taking it last, but somehow still avoiding this numerical problem. And it's not obvious that there was something that would do this. But from discussions with Antonio in the past, I had a hunch. And the idea is to realize minimal model correlators using the Coulomb gas forms. So in the Coulomb gas formalism, instead of these Katz-Stable operators, you would use exponentials, where you exponentiate some free field. Recall that this alpha parameterization. Yeah, so if you want the conformal weight to be HRS, what does alpha RS have to be? Well, it's equal to this, where the scalar dimension for alpha plus and alpha minus are 1. So these charges are what solve the quadratic equation for marginality. And Datsenko and Fiteyev used these exponentials in some contour integrals to get formulas for Virasoro blocks. Something you can also do is to find non-chiral vertex operators, which can be integrated over all of space, thereby giving you a 4-point function on the nose in principle. The integrals are very difficult, but formally the equivalence of these two procedures has been shown using tricks very similar to what KLT used to drive double copy and string theory.
Sorry, I have a very nice question. So you said you're using a free field here, right?
A free field theory deformed by some screening charges.
I see, because if it's just a free field theory, then of course the central charge is 1. But here it's less than 1. So there must be something else.
There's a topological term which shifts the central charge. It's like the Ricci scalar times the field.
Well,
yeah. Yeah, I have 15 more minutes, so this is going to be very schematic, unfortunately. But the idea is that a 4-point function. In the Coulomb gas theory. Oh, maybe the integrals over space. It's equal to an integrated 4-point function in the free theory, where you integrate over the positions of the alpha plus and alpha minus charges, which are inserted such that the total sum of the alphas is equal to 2 alpha naught, where the central charge is 1 minus this. And when you know that this is central charge, then alpha minus is going to be this square root. Alpha plus is going to be that square root. So the large M limit we're interested in is the limit where alpha plus and alpha minus become 1. And what happens when we do conformal perturbation theory using correlators that are expressed like this in the limit of alpha plus and alpha minus equal to 1? Well, a correlator we might like is going to be an integral over these screening charge positions. But it's a conformal integral because these screening charges are marginal. And when you have a conformal integral, you can use Szymanczyk's formula, which takes you from, say, like from star-like configurations to triangle-like configurations. And gammas satisfy this constraint. Okay. So this was not a talk about holography at all, and yet we ended up with melon space, which appeared in Parajat's talk and also Arnav's talk. And that means you can trade these conformal integrals over screening charges for some big melon integral. So this is going to have a whole bunch of melon variables. It's going to have z to some power, 1 minus z to some power, and then a bunch of gamma functions. Or the arguments are all functions of these melon variables. And now the integral of the 4-point function, which we were previously doing numerically for many finite values of m, is actually doable on the nose because you're just integrating this, which is a very easy finite integral. Okay, you're integrating this where the powers are shifted because you don't just have a minimal model correlator, you have a generalized free field, which is multiplying this. So you integrate this, And then you have this big Mellon integral, and you want to approximate it at alpha plus and alpha minus going to 1. Now, if these gamma functions were more generic, setting alpha plus and alpha minus to 1 would not buy you anything, because the large M limit of this would just be, again, a big Mellon integral where you set certain parameters here to certain values, and you would still have no hope but to do it numerically. But the nice thing is that these gamma functions know that the alpha plus alpha minus going to 1 limit is very special, because that is what makes these Coulomb gas integrals local Feynman integrals with integer powers instead of fractional powers in the propagator. And what that translates to is an alpha going to 1 limit, which makes the contour pitched. So you have to do some regularization. And the way to do that is to first set the alphas to more generic values, move the contour out of the unsafe region, which picks up some residues, and then take the limit. And if you do that, the residues you took, which are simpler than the full integral, will actually dominate, and you just have to see what those are. And those give you the coefficients in the beta function and the anomalous dimension. Now that's a rigorous proof, or as rigorous as the Coulomb gases.
Here's some fancy middle amplitude.
Yeah. So this. Yeah, so a Mellon integral for a 4-point function has 2 cross ratios. This is going to have a ton. It has 2 Mandelstam variables. This is going to have a ton of Mandelstam variables. So you choose 2 to be the ones that define the Mellon transform, and then the other n minus 2. That n minus 2 fold integral itself will be the Mellon. So this, yeah, I should write a reference that does this in great detail. It's 2 Joaos and Sasha.
But the position space integral is literally just a larger contacting. Or not. The original position space integral derivative, it's really just a contact. Yeah.
Well, if you were doing this once, it would be just a contact integral, but you have to do this many times.
Okay.
And that's actually a source of major slowdown. So in the chiral case, if you're just looking at Virasoro blocks, you can find somewhere there's a single screening charge, and then you just use this once. For the phi 1,2 chi flow, you have to do this twice. You have more Mellon integrals, and you can still do the regularization and pick up the reg residues and get the right answer. For phi 2,2 chi, you get even more integrals, and then it's just hopeless to do by hand. You would pick up a residue which would reduce the number of integrals by 1, but you still get many, and you still have to take residues for all those, and you get this exponentially expanding tree. So what we used was a package from 2005 called mb.m, which automates this. And we could run it for hours and get computer-assisted proofs of the large M coefficients in the phi 2,2 chi flow as well. And we were happy. So
does the computer assisted proof give you like I mean, are there irrational numbers involved anywhere, or is everything rational at the end of the day?
well, it's the coefficients I was writing with pi's and pi squareds. So there was like 3 8s, pi squared. And yes, we got that. And then we could also do the subleading order with this package. And that had a log 2 in addition to pi.
I see.
And we expect that that after a certain point, we would no longer be able to avoid numerical intervals, and it would become much more complicated. So it still is a matter of luck that the first few coefficients are so simple. But yeah, I guess we started late, so
Yeah, 5 is 7.
yeah, 5 minutes should be fine. Yeah, so now I just want to take a step back, because now that we have now that we have some long-range minimal model, where the large M limit is nice, there should be things we can do with it. So one of them is using this perturbative data to compare to the numerical bootstrap and verify this conjecture, but proof or disprove the conjecture that the kink is right where the long range minimal model should be. But another thing is to go back to the original motivation of saying that now that we have a nice large M limit, can we start proving dualities? So for the phi 2 chi flow, there was this flow and there was this flow, which got us to the same fixed point conjecturally. For phi 1 2 chi, it's not clear what duality you would try to prove. When this becomes strongly coupled, what's the weakly coupled description? We don't know if there even is one, let alone what it is. But there is some unreasonable effectiveness of minimal models that has been observed in the local case. So Zamolodchikov found this staircase flow, which goes from one minimal model to the next when you perturb by phi 1 3. So m plus 1, phi 1 3, it goes to a lower one. And because these are unitary theories and you have a C theorem, it's inevitable that you have to get to the lower one if you get to CFT at all. But in the non-unitary case, there's work by Federico and Stefano, probably some others, showing that you can perturb by other operators and get from a non-unitary minimal model to another non-unitary minimal model, not some other CFT. And that was very surprising. There are hints that our notions of integrability might not be general enough. So if this kind of thing extends to the long range case, so minimal models along with generalized free fields like to close among themselves, then we might imagine that there's some other minimal model, some other Katz table operator, a generalized free field of another dimension showing up here. So it would be nice to get a feeling for what might happen by doing some non-perturbative checks. And a nice thing you can do non-perturbatively in 2 dimensions when you're perturbing around a solid theory is Hamiltonian truncation. So I propose searching for another description using Hamiltonian truncation. And we could even ask about other long range models in 3D, because when I talked about the long range Ising model, I was always writing sigma times chi. But another thing you could write down is epsilon times chi. And we don't know what this flows to. But I have a suspicion, which is that if you look at operators starting off in the decoupled theory, where you have the GFF and you have the Ising model, you have epsilon, which is right around 1.4, and then this has to be marginal, so you have the generalized field, which is right around 1.6. These start to head towards each other, and they probably repel. And then very soon, you'll get to the point where these are 1.4 and 1.6 again. So it's possible that as you dial the coupling here and start to make it large, it becomes literally the same theory where the coupling is very small. So some kind of S value. But that is a very bold conjecture. It could easily be wrong. I hope it can be checked. That's I think, a good place to stop. Thank you.
Thanks, Connor, for the very nice talk. Questions?
Did you check this for QR and some
I think Dario and Finley are working on some Behan version of this. I don't really have an expectation of this there. But yeah, it's true that there's a known window against the description, like phi cubed. So it's, yeah, there should be some story.
Okay. So in this plot, so you plotted the dimensions of those guys. So
Yeah. As a function of S, you might say.
is there a reason why they don't level cross?
Well, I believe in nothing level crosses. So maybe they do.
So if you, okay, coming back to the Ising case where let's say you couple with like the first way, sigma times pi, right? So you said, of course, there's this sweet window in S where it flows to some long range minimal model. So how does the anomalous dimension eta change? Because for the Ising model, it's whatever, 1/4 or something. So does it decrease as you?
Yeah. So it would decrease all the way to 1/4, and that would be precisely where the sigma chi operator becomes irrelevant.
I see.
And it decreases linearly because it's yeah, that critical exponent belongs to a field that has a non-local kinetics.
So maybe it's a good time to just close the session. Thanks, Conrad, again. For feedback. Start.
I'll